Hello, everyone. Hi, everybody. Welcome. My name is Era Memishazuju, and I'm a senior research specialist. Lost our recording. Hi, everybody. As I was saying, my name is Era Memishazuju. I'm a senior research specialist here at VTTI in the Division of Vehicle Driver and System Safety. We also have Laurel Glenn, who is the program manager for safety. We appreciate you joining the webinar on lane change hazard analysis using radar traces to identify conflicts and time to collision measures. You have all come into the meeting muted, and we would appreciate it if you stayed muted until the Q&A session at the end. Captions will be on for your convenience. The videos will be off during the presentation to maintain bandwidth strength. If you have any questions during the webinar, please go ahead and type them in the chat box and we will address them at the end. At this time, I'd like to introduce our presenter. Balachandar Guduri has been working as a research associate since October 2021 in the Division of Data and Analytics at VTTI. He received a PhD in engineering mechanics at Virginia Tech and an MTech mechanical system design at Indian Institute of Technology. His research interests include data analytics, engineering mechanics, control systems, autonomous vehicles, and numerical modeling and plasma spraying. I will go ahead and hand it over to Balachandar for his presentation. And if you could please remain muted and keep your cameras off for bandwidth purposes, that would be great.
Thank you. Thank you all for coming to this presentation. So today I would like to discuss lane change hazard analysis using radar traces to identify conflicts and time to collision measures. So this is the first project I worked on, worked on on transportation area. In VTTI, I joined as like a student, started working on before graduation. And from this project helped me to not only financially, but also like to give like a good understanding in the research areas related to transportation. Also helped me to get a full-time job at VTTI as a research associate. So the application here is in like a signal lane changes for conventional mirrors and also for using a camera-based systems. So camera-based systems, basically the analysis carried out to support federal motor vehicle safety standard 111 rulemaking efforts to investigate lane changes using a camera-based systems. Currently, these are prohibited. So the studies analyze the safety and relative performance of these systems to the conventional mirror systems. The previous research at VTTI conducted investigating using these systems from the naturalistic driving study to investigate the system influences on driver perceptual judgment to support lane changes, decision such as vehicle detection, distance, closing speeds and conflict, etc. under various driving conditions. For example, like a day and night time operations. Also focused on driver acclimation and reliance on the camera-based system, the impact of camera-based systems on the driver eye glances and behavior, for example, like frequency and the duration of these eye glances compared to the conventional mirror systems, and also the potential driver adaptation and unintended consequences. Furthermore, the influence of the moderating factors such as the driver age, system experience, environmental conditions, etc. on the performance, and finally usability and driver acceptance of camera-based systems. The results found that camera-based system increases the driver field of view relative to conventional mirror. Also helps to significantly reducing or eliminating blind spots and increasing vehicle detention rates detection rates and leading to fluid conflicts. However, from the control tests, the solo reliance on a camera-based display can make it harder for drivers to gauge vehicle distance and closing speeds to support lane changes. But during the naturalistic driving scenarios, the drivers are found to use multiple information sources, for example, a rear view mirror or over the shoulder glances to make the decision on the lane changes. And drivers also found that the location and also the screen size have an effect on the lane change decisions, and also the glares in the night time, it can be created some annoyance. So the objectives for the present work here, which is the work is using the data collected from the previous work. So using the data mining an existing set of radar data surrounding real world lane change events, and from the significant part of the this presentation focuses on how this data mining is carried out. And next, using the after this task, so lane change conflict and hazard analysis is investigated using a time to collision values for these lane changes. So I'll provide a brief overview of data collection carried at VTTI. So overall, 36 drivers were participated. These were from Southwest Virginia and are also Virginia Tech employees, non-technical staff, ranging from 25 to 63-year-old. Among them, 50 are female, 21 are male. This study was carried out for 1 month in 2 phases. Phase 1 entirely on the conventional mirror. The lenses carried using a conventional mirror. And the phase 2, these conventional mirrors are replaced by a prototype camera-based systems. These are provided by the OEMs. 3 OEMs are participated in this study. On the 3 types of a light vehicle fleets considered for this study, and around 90,000 miles driving data was collected. Excuse me. And so all these vehicles are equipped with a VTTI proprietary data acquisition system called as FlexDAS to capture and record time-synced video and parametric measures from a key start to a key off for entire trip. And among this, the information of a vehicle network such as vehicle speed, lat and longitudinal accelerations, yaw rate, steering angle, turn signal indicator, GPS data, transmission gear state, brake and also acceleration pedals and etc. are recorded, measured, and also the lane marking information is recorded using a VTTI road scores sensor, which basically developed using a custom mission vision process. Also, several video footage captured using multiple cameras mounted inside and outside the vehicles. Furthermore, following vehicles informations are required using 2 rear-facing corner radar sensors. And these sensors are continental radar PLC units with a short range radar and having a frequency of 24 Hz with a very good accuracy in the range and speed, and have a field of view 75 degrees plus or minus, and can detect objects within 100 meters, and also simultaneously can track information about the 40 targets. And the radar units were configured in such a way that the vehicles located in blind spot in the rear and next to the lead vehicle were continuously recorded. And some of the variables measured from the sensors are a range, that is a relative distance between longitudinal and lateral, and also their velocity components, and age, length and width of the object, orientation of the object, probability of existence, and like in 0 to 1 of that object, and some other like parameters. So overall, using the data from the indicator, turn signal indicator on and off, approximately 25,655 lane change events are identified, and among them are like 12,695 related to the camera-based systems, and also these are like have like a left and right signals association, and also with the time of the operation, and with respect to the vehicle wise, and also the subject wise too. Here the several key points are like landmarks surrounding this signalized lane change events were identified. For example, first one is like the timestamp at which the turn signal is on, and also the timestamp at which the side like tires touch the lane boundary, and also the other tires cross the boundary of the lane. That is like a crossover point, lane contact point and crossover points, and the timestamp at which the signals are off. So during this timestamps, the safety metrics are extracted. But in this presentation, I'm presenting only at the contact points. So first we'll see lane change duration between these timestamps. For example, the time duration between once the signal is on to the car, like vehicle is touching the boundary. And here we can see that the mean approximately this is like for 3 seconds, and also for like a 3.45 for mirrors. And we can see the distribution of these events. And from here, like I don't see any difference between the camera or mirror. Furthermore, like the duration between the contact time to the crossover times, which are approximately like 2.5 seconds. And also it suggests like there's no obvious difference between the camera and mirror based lane changes. And that's for the sedan one. Yeah. And here like for a semi truck, for all these like vehicles have like a different configurations of the sensors, like which are like basically developed by the OEMs, and I'll have like a different screen size and the location they kept. So there will be like some like changes in the like specifications, how they mounted and what kind of screen sizes. We haven't done anything to change that the specifications. For the truck, the times are like approximately 3 seconds between the like signal on to the contact point, and from contact point to the crossover point, it's approximately 2.6 seconds. And also we can see that like there is not noticeable difference between these two types. And also for sedan B, here the times are like 3 seconds and 2.5. So if we can see here, like we can see here from the subject wise, the duration of the lane changes for mirror and camera based for left turns. And it's very hard to see the comparison between the cameras and mirror, but I just wanted to see the variability with respect to the subject wise. For example, there are like some drivers like forget it to switch off the lane, like switch off the signal indicator even after completion of the lanes. That's why like some of the cases like events the duration is more than 10 seconds. And but the overall the in that scenarios are comparatively low compared to the overall number of the events. And for the right terms, here also we can see the variability of this lane change duration with respect to the subject wise. It's good to have kind of this variability for the analyzing, coming to some conclusion on the usability of the camera-based systems. And from this slide, we can see the duration, lane change duration with respect to the fleet, and based on the number of the miles driven. Here, from 100 miles, 100 to 300 miles, 300 to 600 miles, 600 to 9, and above 900 plus. So there is obviously difference between the mean values of the duration for these fleets, because it's depend on the a car specification and also the mounted the camera-based systems. So the lane change duration for the sedans are much higher than the trucks, but there is no noticeable deviations between the mirrors and cameras, except that very high. Probably you can say that here drivers are used to the camera-based systems, and so in this case we can see that initial phases maybe the drivers not that comfortable with camera-based lane changes, and over the time the signalized lane change duration is changed, decreased, but it's not, this trend is not that observable in trucks or or the other sedan. So now for all these 25,655 lane change events, the first step is first to extract the trajectory, the landmarks of the lane reference time, lane contact time, lane crossover time from the road scout data. And we have used some algorithm to identify when it's touched the lane changes and which were further validated using the videos. And once we have this timestamps, then after using these timestamps, the trajectory of the subject vehicle, that's a lead vehicle, is calculated from road scout data. Basically transform this data into making one a lane as a fixed point, and transferred acquired the trajectory of the lead vehicles, and using this trajectory every point, the radar information, using the radar information, the following vehicles are identified. To first that here we can see that the radar information acquired for a relative distance in x direction and y direction, longitudinal, longitudinal. If I plot it for all 40 objects identified from these two sensors, and for entire trip, we can see this huge data cloud, and the color represents the identified object from from one of these object tracks from in the sensor, and using some preconditions, the data is cleaned, and here we can see that they cleaned the X-range data and also other variables. And the conditions we provided here is, for example, if range and the X and Y directions, and also the probability, which is almost close to 1, which status as a measured are predicted, and as a orientation plus or minus 0.4 radians, and with range of like lateral distance like plus or minus 10 meters. That's a like approximately 2 lanes left side, 2 lanes right side, and has a like a data track for like at least 15 seconds and with a stable as one. So there's like the transfer, the clean data from the raw data is, we can see that these are the traces where the vehicles are presented. And from these traces, next task is to identify the following vehicles. This is for the right radar. Similarly, left radar, we use like the same analysis, and I also observe the left radar like traces from the both traces. Like, hey, one more thing is like for the left lanes, we use the left radar. For right lane changes, we use the right radar. And from the cleaned radar traces, so the following vehicles are identified. So they're like a first reference lane, reference time is identified from the like road scout data and are transferred, and also like located the vehicles within the like 200 meters from the lead vehicle when it's on the reference lane. And after cleaning the data, so the data of these following vehicles along with the lead vehicles are represented like presented in a like bird eye view. So using like a space representation, time representations to see whether like the algorithm is like correctly able to identifying these like following vehicles. So here we can see that the trajectory of the lead vehicle along with the following vehicles, and also we see that the timestamps of the signal on lane contact. And for this like all of these timestamps, the metrics are like calculated, such as the TTC value, time, range. I'll define what is TTC. So velocities of like lead vehicle and following vehicles, and that are validated like using videos. This is one example where it's taking a right turn, and another one is also it's here taking right turns. There is no vehicle in the target lane, but there are 2 vehicles located in the previous lane, and the lane contacts and the lane reference time. So like we can visually see here, and this is also validated using video. And furthermore, here we can see that in example 3, there are several vehicles identified, but the next task, which is the important vehicle, which like has a potential like have a conflict with the subject vehicle, that we call as like a principal other vehicle. So next task is to identify principal other vehicle. For example, like it's taking a right turn, a left turn, then this is the like following vehicle as a principal other vehicle. So for this one, we use like a couple of conditions where it has like at least a time information within the 0.5 seconds to the subject vehicle, and also which whether it's taking right turn, then it has to be within the plus or minus 0 to -5 on the right side, or like if it's taking a left turn on the left side. And if more vehicles are present, then like the closest vehicle is the POV. In this case, this is a object N is the POV. So for all these POV, like overall, like among like 25,000 plus signalized events, among them like 7,425 events have like a POV vehicles, and among them like around like 400 plus events are visually verified using the videos. And for these cases, like 7,000 cases, like metrics are calculated at a lane contact, lane crossover times. So here the time like a radar number, like ranges, like lateral distances, longitudinal distance, relative distance, and also the lateral relative velocity, longitudinal relative velocity, and time to collision. Here we considering first order TTC value that's based on the range and range states. And furthermore, like the TTC values within like 0 to 100 seconds as considered filtered. And that so overall 1,185 lane changes events are identified which has a TTC value less than 100. Among them, like 607 events related to the conventional mirror, 5,708 events related to the camera-based systems. And here we can see the distribution of these events for like across the fleet. And like sedan A has like more number of events compared to the sedan B. And also like left and right turns. Obviously, you can see that left turns have like a huge number compared to the right turns. That's like a taking like this is like a schedule watch. Basically crossing the like front vehicles. So there is no difference or distribution in the for a mirror and camera based systems. Now we can see here the relative location of the identified POV vehicles with respect to the subject vehicle that's at the time touching the lane boundary, and each data point represents a one event. And so for the left turns, so here we can see the location of the POV vehicles. Most of the vehicles are like located at least like a greater than like 10 meters and within 90 meters. There is huge like a gap between the subject vehicle to the POV vehicle, POV, except like a few small cluster. And also the distribution of the like these events across the like with respect to range. And also we can see the relative speed, this absolute speed with respect to the range. And most of the vehicles, the relative velocity is like within like 4 meters per second. And also the TTC value ranging from like 0 to 100. Even the small cluster has like higher like TTC values, which are like greater than like say like 2 seconds, or like greater than like most of them are like 10 seconds. And for right turns, so more like all of them are like located like at least like far away from like 10 meters. And there's a good like TTC, and the velocities are ranging within like 2 meters per second. And also like couldn't able to see like previous like plots the major like differences between the camera based lane changes and the mirror based lane changes. And here we can see the like qualitative and quantitative visualize the location of the POV vehicle with respect to the lead vehicle for across the like fleet, and the mean value of the range approximately 45 meters with a mean is like it's one of the like 1 or 2 is very close to the subject vehicle. But most of the like 95 like 5 percentile of these data like have a distance of like 17 for the sedan, 17 for the truck, and 8 for sedan B. And here for the relative speeds, the mean is approximately 2 meters per second, absolute with a minimum as very like almost same velocity, same speed. And for also TTC, the average, the mean is like here, like approximately 31, 32 seconds, with only 5% of the like whole data has like values of like 8 seconds, like approximately 8 seconds. Now come to the comparison with respect to the like mirror and camera for the mean TTC values. For a left turn, mean is like slightly lower than that for mirrors compared to the camera. Here we can say that so this value is lower under conventional models relative to camera-based counterparts, suggesting that drivers were more conservative when executing left lane changes under the camera configuration. But that's like but when taking the right turns, I don't think like overall the right turn has like a larger time TTC values compared to the left turns. Overall, so the means are like very close, and there is some like a variation in these two aids because of the specification. Might have like some effect of like these camera-based systems, like the specification of the camera-based system might have like a small effect, but if you consider overall, there is no significant difference. And here we can see that from this plot, here the minimum TTC value for each driver is considered, and for the driver overall, like then average mean is calculated. So for overall, for camera and the mirror, they are very close. And also for left lane changes and right lane changes. And also we can see the distribution with respect to the time bins. Like under 5 seconds, like approximately less than 2% like events have like associated with this 5-second bin. But most of the like data is where like TTC has like greater than 30 seconds. So from this analysis, no significant differences in TTCs were observed between the conventional mirror and camera-based system across any fleet vehicle. Combined for left and right changes. Analysis reveals no critical conflict or pattern of ill-advised lane changes observed under the camera displays. Use of camera-based system did not appear to impact the functional performance associated with the making execute lane changes. Of course, it's the camera-based need to be appropriately designed, and with that, these systems can help to detect the potential conflicts because of the wider field of view. Thank you, and I would like to take any questions.
Thank you so much, Balachandar. I'd like to remind everybody as well to use the chat box if you have questions. We're going to be taking the questions at this time.
I had a quick question for you. While the individuals were learning the camera-based system for use of lane changes, did you notice any kind of behavior in their actual lane changing during that time when they're kind of habituating or learning to use the video camera versus the mirror-based system?
Yes, in the previous work, so they emphasize that so there is a control test first to give an exposure to these systems before going to the naturalistic driving. So they're several 1 hour sessions, I think. So which introduces to how to familiarize with the closing speeds and the relative distance between the vehicles. That give us some accumulation to the use of these systems. Furthermore, also here from the questionnaire after the participants after the completion of the study. So indeed, they mentioned that there is some issues with closing speeds, I think, but just solely based on the lane change, based on just only looking at the camera system, but that over the time, using a multiple information from using the rear view mirror and this over the shoulder glance that helps to making the lane changes better for the bird. Also during the light time, the brightness and the glare because of this camera systems have an issue with the drivers.
Thank
So these
you.
are some of the noticeable identified patterns among these drivers.
We have a question from Matthew Conde. He says, I'm interested in any anecdotal experiences people had regarding the new technology. Did study participants perceive the new technology as better or simply different? In other words, just because it was new, were people more trusting of it?
I'm not sure, but whenever there is a technology, I think there is some excitement there, but at the same time, it especially during the driving scenarios, it has a impact on driving, how safe this is, and also there's a scarce fear associated with the new technology, but that only can be eliminated, or the technology to be implemented based on the studies only, and proper education of the technology and the limitation of the technology helps to the drivers to accumulate with the new technologies.
We have another question from Jeff Seekvars. Did either method have more initiated lane changes that were aborted and returned back to initial lane?
Yeah, that's a good question. Yeah, we haven't investigated that part, where lane changes are abrupted, or we are only focused on the complete lane changes where a signal on and signal off is initiated. So that's an interesting area to study. What happened? What are the reasons? The signal lane changes are stopped or they're stopped. We'll study in the future about this area.
Thank you. Matthew has another question. Were the cameras constantly on or only in the act of lane changes?
Haven't actually seen the vehicle, but I believe it's continuously on.
Great. We have a question from Laurie Mostanen. Do you know if there are any similar studies where the vehicles are equipped with concave wide-angle driver's side mirrors, which are commonly used in almost all other countries except in the US?
So concave traditional mirrors or concave traditional mirrors, yes, but I haven't studied them. Yes, there are available literature with concave. I read about some, but haven't studied in deep.
I have a question too. Compared to traditional rear view mirrors, would there be any eye strain or visual fatigue from long periods of electronic visual display viewing?
I believe yes, but we haven't studied that area. But that's also one of the interesting area to and importance to study furthermore, which will be a future scope. but I believe that like there will be some strain in the eyes for long exposure, and how it can be avoided need to be investigated further.
I believe Laurel has a question.
Yeah, sorry, I can't for some reason get the chat box working on my end. But could you discuss more on the like, were there a lot of, or in greater detail, the fields of view differences between the two systems? Or was there any difference, or were they pretty similar?
Yes, there is a difference field of view, like I don't remember like on top of my head like the day like actual like field. There like a field of view is like approximately I think 30 to 50 degrees, but yeah, that like provides like that helps to avoid the blind spot, which like very difficult for using the conventional mirrors. But what is the like field of view? Basically, I think it depends on the manufacturing specifications, and all this across this these three fleets used to have like a different, slightly different field of view. And this field of view can help to like identify like any potential vehicles in the blind spot.
Are there any issues associated with like the lane change patterns when the driver is getting used to the camera-based system?
Yes, some, but like not significantly. Like initially, like it takes some time to like first 100 miles and 200 miles. It took some time to accumulating the this like camera-based systems, but after that, I think at least the results like from TTC values, it doesn't emphasize any differences, but there like some for example, like only I think in the night time from the previous report, it suggests like the issue of like glare and like the brightness have affected like their driving, but not on the pattern.
Gotcha.
Driving pattern.
Checking the chat box to see if we have any other questions. Okay, it looks like we don't have any further questions at this time. If you do have a question, please feel free to type it in the chat box. I would like to thank everyone again for joining the webinar. This webinar will be uploaded to our YouTube, and I will notify everyone via email once that is complete, so you'll be able to access it. Registration is open for our next webinar. The next webinar will discuss how autonomous vehicle technology can become a first-line mobility option for people who are unable to drive, such as older adults or people with disabilities, while also reducing the cost of transportation for both individuals with special needs and municipalities. This webinar will give municipal leader transportation professionals and researchers a better understanding of how AV deployment can serve American small towns. I will provide a link to also the registration for our next webinar. If you are interested, I'll put that in the chat box. And thank you once again, everybody.
Thank you. Thank you all.